As you know, Earth applies gravitational force on different objects, and due to that we have the concept of weight. Earth is not homogeneous, so while we take G to be 9.8 for our purpose, G cannot be 9.8 at every single point on Earth's surface. Earth also pulls Moon, for example, the man-made satellites, for example, at those distances. The gravitational force, which follows inverse square law, should be even lower, and therefore the value of G at those points would be lower. With depth also, if somebody manages to dig a hole significantly deep, then as one go deeper into Earth, then also the value of G changes. There is one more effect, which is the rotation of Earth. Suppose one observer is analyzing somebody somewhere here. Observer is also on Earth. The object is of course on the Earth. Earth is spinning. That observer will say that this object will be pulled by the center of the Earth, Earth pulls objects from its center, and that force is mg. That G is the pure G, which you can call 9.8. But that observer will also apply the centrifugal force, and centrifugal force should be away from the center of the circle. Different people on Earth's surface move on different circles. This fellow is moving on this circle, and centrifugal force should be in a direction opposite to the center, this one, and that will be mr omega square, where r is not the radius of the Earth, but r is the radius of this circular path. Omega is same for everybody on the surface of the Earth. In fact, even inside, whether equator or above or below, omega is same for everybody. R will change. The net force that is applied on that particle, that net force is ma. From Newton's second law, net force is ma, and it is this A which can be thought of as G dash. So effectively speaking, the force that is applied on that object is mg dash or ma, and because of this, mg dash normally won't be mg. ma is the resultant of these two. To find the resultant of the forces, one needs angle. mg will pass through the center. So let's say this angle is theta. This angle is 90 minus theta. What is the angle between the two forces? (90 plus theta). So just use this formula, F square equal to P square plus Q square plus twice PQ cos of the angle between the two vectors. And when you do that, then you get mg whole square plus mr omega square whole square plus twice mg mr omega square cos of 90 plus theta is minus sine theta. Now as far as small r is concerned, this is capital R, this is 90 minus theta. So small r is capital R sine theta. So it would become bigger. Right? Now this F is mg dash so m square can be cancelled. One can take under root and that will give g dash. Now practically speaking, the effect of this centrifugal force is not much. In comparison to mg, this effect is not much. Now, why is it not much? Because omega is quite small. Just to have a feel of its size in comparison to mg. Now your weight, let's say your mass is around 50 kg, so we are comparing it left side with something like 500 Newton, right? Now, mass 50 kg, radius of the order of 6400 into some decimal. So 50 into 6400 into some decimal, and then omega square. This is the key. Omega is given by 2 pi by t. Why 2 pi by t? Omega is angle upon time. Angle is the whole circle, 2 pi radians. Time is 24 hours. Look at this now. 24 hours. And square of that. That is the key. Omega is small, but omega square is very, very small in comparison. So let's look at these. This is 10 to the power 3. Let's say 10 to the power 4. Pi square is around 10. 3, 4, 5, 10 to the power 5. Now 24 into 3600. Ten to the power square of that. Ten to the power 5 square, right? Yes. Yes, I heard something, hand raising. Just compare this to this. Inside the bracket, sine theta, some decimal. In fact, decimal will make it even smaller. So even if we ignore its contribution, even then things are really bad in comparison to 500. So the moral of the story is that it's really small in comparison to mg. You can, now in this particular diagram, it may look as if it is significant, but if I show it too short, then it won't look clear. If I try to show it on scale, it won't look clear at all. So actually speaking, that vector mr omega square should be very tiny in comparison to the vector mg, and the resultant of the two, ma, that should be very close to mg. mg is too dominant, so resultant should be very close to mg. That is the real thing that happens. Now you can, mg mr omega square, so you can tell the angle also at which ma will be there. Now, when is the effect the greatest? If we take sine square theta common here, in fact some more things can be taken common. Omega square can be taken common, r can be, and of course sine square can be. So we would have twice g minus omega square r. Now we discussed here that mg is much bigger than mr omega square. So that's why I put a minus outside. It is g first, then omega square r next. And we know mg is much bigger than mr omega square. So 2g minus omega square has to be positive number. Sine square theta is positive, g r is positive, omega square is positive. So clearly g dash square is g square minus something positive. So g dash is smaller than g. Now effect of theta. If you subtract larger number, then g dash will be shorter if you subtract larger number. Theta is the angle from vertical, and sine theta is maximum at 90 degrees. That means at equator theta would be 90 degrees, sine theta would be maximum 1, the negative subtraction will be maximum, and g dash will be minimum. So people who are living at equator, they should be weighing less. But you know how less it is? Hardly anything. From practical point of view. And on the other hand, at poles, theta is 0. If theta is 0, sine theta is gone. G dash is g. At the pole, there is no effect of the rotation of the earth as far as apparent weight is concerned. If you take a globe, you turn it, put your finger at the top, you would not feel any effect. Take a globe, turn it, put your finger at the top, no problem. But try to put your finger at the equator, globe will try to drag your finger due to friction. So at pole, the effect of this rotation is not really seen. So due to the spinning motion of the earth, g is maximum at the poles and minimum at the equator. There is one more reason why g is more at the poles. Poles are closer to the center of the earth. You know, earth is somewhat flat. The poles are somewhat closer to the center of the earth. Closer means larger force. So both these factors make g greatest at the poles. This result is big, but for equator, one can put sine theta equal to 1, and one can arrive at a simpler result at equator. So when you do that, So in the case of equator, we have this result, g dash equal to g minus omega square r. So what is somebody's apparent weight? Mg dash. Any question? Let me know, or we proceed with applications. For the sake of theoretical discussion, one can also analyze this situation. On the earth, suppose some object on its own moves rapidly. Earth is moving fine, that's one thing. But suppose some object is also moving, maybe some train. Imagine some train traveling very fast like this. So, in that case, you see in this derivation, for this object, the observer applied centrifugal force mr omega square, because all of us are moving with omega, because we are moving with the earth. But if somebody starts running, okay, running speed is too small, you still say ignore it with respect to earth's speed of spinning. But what if train's speed becomes somewhat comparable, or suppose we are discussing it for the sake of theoretical discussion. In that case, the omega of the object also needs to be taken into consideration. Here is a problem based on that. Good question for thinking purpose. Only one option is correct. Let me check. Earth is rotating in what way? East to west or west to east? Are you sure? East to west? West to east. Now this is for theoretical discussion. So you have to give a very strict answer. Now think about this. You are on a ship and you are running to the right side. Well, head is too big. Anyway, you are running to the right side. Ship is also moving to the right side. Suppose this is B and this is small v. What will be your speed with respect to somebody stationary outside? Let me clarify. Capital V is the speed of the ship with respect to this person. Small v is your speed with respect to the ship. Small v is your speed with respect to the ship. Capital V is the speed of the ship with respect to this fellow. So what is your speed with respect to this fellow? Let me write. Small v with respect to ship. Capital V with respect to O. So what is your speed with respect to O? Yes. V minus V. Are you sure? Let me try to do a video demonstration. Or you can also do it. Take some book, keep some eraser on it, and then move the book and move the eraser also in the same direction. Eraser is here. Move your hand quickly like ship. Eraser is on that book. Eraser is also moving slowly, let's say. Book is also moving. Aren't we traveling with great speed because of Earth? We are on a big ship, Earth ship. Now, if that doesn't look too clear, then go for mathematics. Go for mathematics in that case. Use the equation of relativity. Velocity of the particle with respect to observer is velocity of particle with respect to the ship plus velocity of ship with respect to the observer. This is the ship. This is the observer. This is, let's say, particle P. With respect to the ship, it is going with V. Ship with respect to the observer is going with capital V. Look at that. So if you are on a ship which is going to the right and you start running on that ship, then somebody from outside will say your speed is even more. V plus V. This situation is not like that situation where you subtract one motorcyclist, other motorcyclist, VA, VB. In this case you subtract. This situation is not like this. Observer is not moving. Here VA will say what? Here VA will say what? B is going at what velocity? VB minus VA or VB plus VA? Here the answer will be minus. Here observer is moving. Here where is the observer moving? So they are different situations. Just like that. Omega. In one case, now Earth is moving from west to east. In one case, train is going, let's talk about train B. Train B is going from west to east. That train has small omega and that ship has big omega. Well, actually big omega is like this. But anyway. Now, what is the speed of this train with respect to O? Omega plus omega. Look at this discussion. Higher omega means higher centrifugal force. We are talking about equator here. Okay. Fine. So if I take this point into consideration, this is a centrifugal force. This is the Earth's attraction mg force and normal reaction. This is a normal reaction. Centrifugal force plus normal reaction should be equal to mg. The normal reaction is mg minus centrifugal force. If omega is more, effective omega is more, centrifugal force is more. That means n should be less. F2 is less. How about F1? In case of F1, centrifugal force is going to be smaller because omega will be, effective omega would be this. Or if you like, write it like this. It is a square in centrifugal force. It is a square which comes. So what minus what won't make any difference. Centrifugal force will be smaller in this case, and therefore normal reaction will be more, isn't it? Option A. Any questions? Let me know. As we discussed, what is the situation right now? Situation right now is that if theta is more, g changes, g dash that is, theta less, theta more, g is different at different places. So g dash has different value if Earth stops rotating. Then the rotation effect will be gone. So that means if at equator its value was less, what will happen? It will become more. It will become more. If it was less here at some angle, because of rotation, it will become more. At the poles, well, there was no effect earlier, same. So what's the best option? It should increase at all places except the poles. That means option D should be the best choice. Any questions? Let me know. This is just the extension of our circular motion discussion. Imagine uniform circular motion taking place. So the particle is traveling like this, round and round, but due to some reason it is also given a constant upward velocity. So while it continues to perform circular motion, it also travels up. When you superimpose the two motions, you get this type of structure called helix or spiral. It's like spring. If you consider this point, for example, and then this point, then it is like one circle done. This is what this should have been from here to here. But when that circular motion was going on, a push was also there, or let me say a speed was also there here, or velocity was also there up. So it looked like this. You come across superposition of motions on many occasions. Think about cycle for example. Cycle tire cannot be performing pure circular motion. Pure circular motion means how can it move forward? In pure circular motion, things just go round and round and round. They don't move forward or backwards. Net. Average, if you see, there is no displacement in circular motion. But in case of cycle, that's not the case. Or why would anybody use cycle? You want net displacement to take place. So, in case of cycle, the net motion is not circular. It is circular plus translational motion also, forward direction also. So when cycle goes from one place to the other place, all parts on the rim also travel, but they can't go straight. They have to go round and round also. So it is a superposition of two motions, circular motion and forward motion. In case of helix, the circle was like this and the vertical was like this. It was like saying that the center of the circle, that upward was passing through the center of the circle. Here, it is something else. And in this case, the motion of a particle is somewhat like this. It's called a cycloid. Cycloid is a mathematical curve, just like spiral is a mathematical curve. Cycloid looks somewhat like this. So a particle does not perform circular motion, but superposition of two motions gives you something like this, called cycloid. But right now I'm talking about helix. So a circle pushed in perpendicular direction. A circle pushed in perpendicular direction gives you helix. A circle pushed in this direction, not perpendicular, that gives you cycloid. Now that was the background. Here is a problem based on this. More than one option may be correct, though it is not necessary. The question is typed below the figure. In circular motion, how can acceleration ever be constant? Its direction changes all the time. It's towards the center. Yes, because it is uniform circular motion, upward motion is no problem. Upward motion is no problem. Circular motion is uniform. That means centripetal V square by R will be same. That means magnitude of acceleration will be same. There is no tangential acceleration. Option C should be correct. If you have any questions, then let me know. Regarding A, how can velocity be constant? Look at different points. Isn't direction different? Anything else? If V is not constant, then how V square by R is constant? Vector V is not constant. Vector V is not constant. But V square by R is not vector V, it is the magnitude of V. That's why vector V is not constant, but V is constant. That V is constant. Particle is going upwards, so shouldn't it accelerate along y-axis? Shouldn't acceleration decrease along y-axis? If you fire a bullet and it goes with constant speed, why should there be any acceleration? Question says that particle is going with constant speed. It is going with constant speed. So why are you worried about gravity? Somehow something is done, maybe somewhere in the space. Yes, any other question? And this type of motion is very common in magnetic field, where you can take charged particle like electron, and in case of electron we often ignore gravity. Effect of gravitational force is negligible on electron. Yes, anything else? This is your assignment question, and we stop at this point.